Hello, and welcome to the Chapter 7 extra video. In this one, we'll be talking about divisibility rules. The main goal of this video is to learn how to express an arbitrary positive integer in terms of its decimal expansion, to write it out a certain way, and then to prove divisibility rules using this. So divisibility rules like an integer is divisible by 2 if and only if its last digit is even. This one you probably know. This is how you know if a given number is even or odd. You really just need to look at the last digit. Or then this one maybe some of you know, maybe some of you don't. Integer is divisible by 3 if and only if its digit sum is divisible by 3. So if you add up its digits and that number is divisible by 3, then the original number was divisible by 3. And you likely don't know this divisibility by 11 one. This one's pretty interesting. An integer is divisible by 11 if and only if its alternating digit sum is also divisible by 11. So similar with 3, but this time an alternating digit sum. So we'll learn what all these things mean, and we'll prove these results. Let's get started. So before we get started proving some of these divisibility rules, we need to talk about what it means to write an integer. So for example, when we write the integer 5,117, just listen to how I say that, right? Each digit and its location in the number have a meaning, right? This is something we learn way back in middle school or elementary school when we learn about place values, right? Each digit can be a place value. And for most of us, we kind of lose that thinking along the way until we come back to a class like this, and we get to use that thinking to prove some really interesting results about divisibility. So I'm going to write it down, 5,117. And just by how I said it, it's 5,000, so 5 thousands, right? 10 to the third is 1,000. 5 thousands, 100, so 1 times 10 to the 2, 10 to the 2 is 100, so 100, and 17. Okay, 17 is a bit weirder, but we know that 17 really means 7 and a 10. So that is 1, 10, and 7. And this we could write to follow the pattern 10 to the 0. This is the ones place, the tens place, the hundreds place, the thousands place. I'm just writing those out as powers of 10. So being able to do this is actually going to be really, really handy as we move forward in this one, to be able to write an arbitrary integer like this. So the deal is that each digit represents a coefficient of 10 to the k. Every single digit you see is a coefficient of 10 to the k for some non-negative integer k. So k here would just be how many digits the number has. And this is called the decimal expansion of an integer when we do this. So just given an arbitrary positive integer, we can define these new variables a sub I, where a sub I is the coefficient of 10 to the I for each I in the decimal expansion of a. And so, like up here, this would be a sub 3, a sub 2, a sub 1, a sub 0 are those digits. And so in general, we could write this, an arbitrary positive integer written as, using these a sub i's, a bunch of multiples of different 10 to different powers is what we have here. So that'll come in handy. It's also going to be useful to consider the digit sum. So if we take all these a sub i's and we just add them all together, so if we perform this operation on the a sub i's, so add them all together, that's going to be a useful thing to look at. Another thing that would be useful to look at is the alternating digit sum. So just you would be like a1 minus a2 plus a3 minus a4. So instead of just adding them all up, we alternate positive, negative. That'll be useful too. All right, let's see what we can do with this. The idea is to take that result, that idea that we can express a positive integer in that way, and combine it with a couple of laws of logic, or laws of divisibility that we've been looking at in section 7.1. And so you're asked to prove this result in the homework, chapter 7, section 1. Let a, b, and c be integers with a not equal to 0. If a divides b and a divides b plus c, then a divides c. I'm going to call that 1 star because we'll use this later. We've also proven in the last video that if a, b, and c are integers with a not equal to 0, if a divides b and a divides c, then a divides their sum, b plus c. So with both, I'm going to give that one a double star. All right, yeah, because I'll use those later. So using these two things in conjunction with each other, and using the fact that we can write a positive integer as powers of 10, multiples of powers of 10, the decimal expansion. So let's take a positive integer, x, write out its decimal expansion, and we're going to use these two results to prove something about it. So notice what we can do here. So each of these 10 to the k's, 10 to the k, 10 to the k minus 1 up to just 10, those are all divisible by 2, right? 2 divides 10 to the k for every positive integer k, and that's simply because 2 divides 10. So it'll divide a power of 10. So 2 divides all those. So if I kind of group these guys together, then I know I can write this as 2 times some positive integer. What should I call it? 2L plus x 0. So I could write x like this, since I know that that part is divisible by 2. That is, 2 divides that whole big sum. So that's why I have it written as 2 times L. And now how I can use these two results, these two previous results, star and double star, is that I can say, so like think about this first part as b. This part, think of this as like b, and x naught as like c. Yeah, I'll do a different color for those. So call this part b, call this part c, and let a equal 2. As in up here, letting a equal 2, and here. So we have then that 2 divides b, and if we assume that 2 divides the whole thing, so over here then would be b plus c. So if we know that 2 divides b plus c, if 2 divides x, then, or if 2 divides b plus c, and we know that 2 divides b, so that's this bit, so we know those two things, then we can conclude that 2 divides c, x naught. So if 2 divides this one and 2 divides this one, then 2 has to divide this one. So that is, if 2 divides x, then 2 divides x naught, because we know this one is divisible by 2. And we can go the other way with this. If we know that x naught is divisible by 2, well, that's x naught's like c, so that would be this one, 2 divides b, and 2 divides c, then we can conclude that 2 divides b plus c, or x. So we have both directions here. 2 divides x if and only if 2 divides x naught. And what is x naught? X naught is the last digit of x. And so that's the result. And that's that first divisibility rule for even numbers. As I said, we just proved this divisibility rule. Integer is divisible by 2, that is, it's even, if and only if its last digit is even, right? We saw that 2 divided x, if and only if 2 divided x naught. So this one's good. We've actually proven this one already. And again, the idea is to use this decimal expansion in conjunction with those two sum divisibility rules. And we'll be able to use this on a lot of these divisibility rules. This is pretty much what they all come down to in some way, shape, or form. Divisibility by 3, we're going to take a look at this one. Divisibility by 5, we'll do that. Well, actually, we won't do that. That maybe I could leave to you. Divisible by 5 if and only if its last digit is divisible by 5. After seeing that last proof, this one should not be too hard. I'm gonna call that as checked off. Divisibility by 7. I think maybe there's an activity problem here. divisibility by 9. So this one's similar to divisibility by 3. You take the digit sum and see if that's divisible by 9. Divisibility by 11, that's that strange alternating digit sum. So we'll see why each of these works, and we'll prove that they're true, because after all, that is what a proof is. It's an explanation for why something is true using rigorous logic and other mathematics. All right, let's prove some of these. I'd be really interested to know how many of you have seen this divisibility by 9 rule. That if you want to know if a number is divisible by 9, you add up its digits and see if that's divisible by 9. And you can keep doing that on and on and on. Keep taking digit sums and see if it's divisible by 9. Because it's a result some of us learned kind of really early on, and then probably either forgot about or it comes up every once in a while. And this class will finally get to understand exactly why this thing is true, why this works. But before we prove why and explain why it's working, let's take a look at a couple examples in case you're unfamiliar with this idea. So, for example, if we take the number 9,117, its digits would be 7, 1, 1, and 9. And so we can compute its digit sum. So this would be 9 plus 1 plus 1 plus 7, or 8, 9, 18. And what this rule is claiming is that since we know 9 divides 18, so since 9 divides 18, 9 also divides 9,117. We can conclude that. And so it's pretty cool. It's a pretty cool little trick. It works even better when we have a much larger number, because this digit sum thing, it really reduces the size of the number that you're considering to a point where, you know, it's just something you know. We know 9 divides 18. So for example, what about like 140,656,716? Compute its digit sum. This would be what? 6 plus 1 plus 7 plus 6 plus 5 plus 6 plus 0 plus 4 plus 1. So that's what? 5, 11, 16, 22, 29, 30, 36. And well, 9 times 4 is 36. So, and if we didn't remember that, perhaps, if we didn't remember that, we could do another digit sum. We could take a digit sum of this. Digit sum, 3 plus 6 equals 9. And so since 9 divides 9, that one's obvious, 9 divides 36, hence 9 divides 140,656,716. So that's how it works. We can keep doing digit sums and keep concluding like that. 9 divides 9, 9 divides 36, 9 divides this whole thing. And so it's really cool. It's a really nice trick. But what's even more interesting is why it works. That's what I really want to get to. So we'll see that in the next slide. First one we'll prove is this, divisibility by 9. And this proof that we're going to see, it's actually something people call casting of nines, is something you might want to look up if you're interested in this. That's what some people call this. So before I get to proving this, I need to kind of establish another statement. And that is that for all what do I want to say? For all positive integers k, so for all k greater than or equal to 1, 9 divides 10 to the k minus 1. So we might be able to prove this by induction. I think that, you know, there's definitely a proof we could do for this, but maybe just writing out this sequence 10 to the k minus 1 will convince you. So maybe if I make a little table up here of k and 10 to the k minus 1. So if k is 1, we're looking at 9. If k is 2, we're looking at 99. If k is 3, we're looking at 999. case 4, we're looking at 9,999. And so it's pretty clear, at least you should be able to see why this should be true in general, because it's just going to be all 9s. We could even prove this using the decimal expansions. Maybe we don't even need induction for this. Just write out this number as a decimal expansion, see that it's all 9s, and clearly 9 will divide that because of how each one of these is. And so with that fact in hand, let's prove this divisibility rule. So I want to make it clear I'm proving the divisibility rule. This was a kind of extra statement. I'm going to just say that. That's proven. That claim is proven, sort of. Okay, so let's let x be a positive integer. Then x equals, we'll write its decimal expansion, x to the, or xk 10 to the k plus xk minus 1, 10 to the k minus 1, x1 times 10 plus x0, the last digit. And what I'm going to do is I'm going to break up each one of these 10 to the k. So 9 divides 10 to the k minus 1. And so each one of these 10 to the k's, I'm going to split into 10 to the k minus 1 plus 1. I'm going to write each one like that. What I'll get is the following. I'm going to write this one on 2 lines to hopefully illustrate a point. So I'll get xk. I'll take the part that's 10 to the k minus 1. I'll take that part off. Plus xk minus 1 times 10 to the k minus 1 minus 1, and so on. I'll keep taking those parts. X1 times, so this would be times 9. I'm just pulling 1, so this would be 10 to the 1 minus 1 plus x naught. X naught doesn't change. And then plus, what did I do with the rest of these, right? I just looked at the, I split up 10 to the k as 10 to the k minus 1 plus 1. So what's left is xk plus xk minus 1. Actually, let me write this out a little bit better. Here's what I want to do. Plus xk minus 1 plus plus x1. And then we already wrote x0 up here. That one didn't change, so I'm not going to write it again. And so together, right, if we look at these sums along the vertical, that will equal xk 10 to the k. So I've split up each one of these terms. Notice how I've done that. And then this would be 0, and that gives you x0. And so the deal here is that, look at just this part. 9 divides 10 to the k minus 1 for each k. So 9 divides each one of these terms, x sub I times 10 to the I minus 1. So it divides the whole sum. So again, we'll think of this whole thing as like B. And then we'll think of this whole thing, this whole sum, as C. And then again, x is B plus C. So I have x written as B plus C. I know that 9 divides B. So since 9 divides B, and using star and double star, so I'll say by star and double star, it follows that 9 divides x if and only if, so we'll use star in one direction, double star in the other direction, like we did in the last one. 9 divides x if and only if 9 divides this sum, xk plus x, k minus 1 plus x1 plus x0. So that is the digit sum. So divisibility by 3 works basically in the same one as the last one. In fact, we could state this result as a corollary, since remember the last result really just hinged on this fact that for all positive integers k, 9 divides 10 to the k minus 1. But since 9 divides that, it follows that 3 divides that as well. And so the entire last argument can be, if you just take 9 and replace it by 3, the entire argument will run. It'll completely work out in the same way, and we'll get the result divisible by 3 if and only if the digit sum is divisible by 3. And so this one is pretty handy too, and is really a corollary of that previous one. It all hinges on this fact. We won't be able to do this in every case for these other divisibility rules. The next one we'll look at, 11, it talks about this alternating digit sum. And so something a little bit different is going to happen there. Let's take a look. So we should first talk about what we mean by alternating digit sum, since that is in the statement of this divisibility rule, right? An integer is divisible by 11 if and only if its alternating digit sum is divisible by 11. So the deal here is if we take the decimal expansion of arbitrary positive integer a, so we'll write it like this using the a sub k's, then the alternating digit sum of a is this sum, so we can write it out compactly using summation notation, or maybe if you're not quite seeing that, you can see it here, right? We'll do a0, so the ones place minus the tens place plus the hundreds place, and so on and so on, and we'll just keep alternating until we get to the end. So for example, the number 1201, we can compute the alternating digit sum for this. That would be 1 minus 2 plus 2 minus 1. In this case, we get 0. And remember that everything divides 0. Since 11 divides 0, this theorem tells us that 11 also divides 1221. If we take something like 1223, we can take its alternating digit sum. Here we'd get, what, 3 minus 2 plus 2 minus 1. So what would that be? That's 1 plus 1. We would get 2. And in this case, since 11 does not divide 2, 11 does not divide 1223. So this is it's a test for divisibility by 11. And we get to do both ways because, of course, we have an if and only if. So really, we're using the contrapositive of 1 for this one. What about something a little more complicated? What if we took a number like 60,258? If we want to test this for divisibility by 11, we'll compute the alternating digit sum. In this case, we get 8 minus 5 plus 2 minus 0 plus 6, which is what, 3, 5 plus a 6 is 11. And, well, 11 divides 11. 11 also divides 60,258. So it's a pretty cool test once you have the hang of this alternating digit sum. And so the proof of this, we'll see this alternating digit sum sort of pop out when we make a little change. Let's see how that works out. So before we see exactly how it works out, we need to first talk about expressing a sum to an arbitrary power. So what do I mean by that? I mean, let x and y be integers. Let's say positive integers. No, it's fine. We'll just say integers for now. Let x and y be integers. Yeah, that's what I want. Let x and y be integers. And n a positive integer, just some positive integer. Then what does x plus y to the n look like? Well, so you might recognize this as like x plus y squared, in which case, you know the term FOIL, or maybe you just remember the formula. This is x squared plus 2xy plus y squared. You might even know how to do it for when n is 3. x plus y to the third is x cubed plus 3x squared y plus 3xy squared plus y cubed. And maybe you even know it for 4. In fact, later on in the class, I'll show you a really neat pattern with this that'll let you do this for any n, and we'll understand what these coefficients are in general. But right now, all I want you to focus on is, in general, what it's going to look like. And so it'll look like x to the n plus some constant times x to the n minus 1 y. We'll hear what these constants are later on in the class. For right now, they're just some constant. It's not going to matter when it comes to divisibility, because I'm going to look at this thing in terms of divisibility by x. So all that I care about is these factors of x. So these constants won't really matter. Plus some constant, x to the n minus 2, y squared. See how the powers always add up to n. Plus, and we'll keep doing this down, 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 down until we get to, say, x. How about just x by itself, x to the first power. So it'll be some constant times x to the first power, y to the n minus 1 power, plus y to the n. And the important thing here is that each one of these terms has an x in it, right? They have a factor of x in it. So I can pull x out of that whole thing. I'm going to let, right, I'll do it, yeah. X times x to the n minus 1 plus some constant x to the n minus 2 times y plus, keep going, last one would be y to the n minus 1. So I've pulled out an x of all those. I still have my y to the n over here. But the important thing here is that this is an integer, because x and y are both integers. And so I'm just going to call that, let's call it z for integer. And so what's going on here is x plus y to the n can really be written as x times some integer plus y to the n. So that's x plus y to the n. And in fact, even if I had a constant out in front of this, it wouldn't look too different. Let's say I had something like a n, x plus y to the n. You'll see why I chose that in a second. Then this would just look like, let's say, x times an times z plus an y to the n. It still remains a fact that this term is divisible by x. And so we'll get this nice relationship that x divides this if and only if x divides this. I'll write that down. X divides. So we're kind of just exploring right now, exploring these binomials. And we've come to this nice fact that x will divide an x plus y to the n if and only if x divides an y to the n. So why have I done something like this? Well, the key to our proof that we're about to look at is going to rely on the fact that I can write 10 to the k as 11 minus 1 to the k. So remember, the arbitrary integer we're going to be looking at is going to be looks like, you know, some coefficient ak times 10 to the k and a sum of a bunch of these guys. A sum of a bunch of things like this. And if each time I can split it up like this, split it 11 minus 1 to the k, then I can sort of take my 11 and my 1 and sub them in for x here. And since I'm talking about divisibility by 11, right? Talking about divisibility by 11, this fact that this number is a multiple of x means that it'll be a multiple of 11. And so we'll just have to be concerned with this thing. Now remember, we're going to have a bunch of sum of a bunch of these things, but this is my takeaway right now, and I'll use this fact here in the proof, that x plus y to the n can be written like this. All right, let's get into the details. All right, let's kind of do a, I don't know, maybe I'll say proof sketch here. If I was actually doing a full proof, maybe I would include some more details in it. Maybe I would prove a lemma with that result on the last slide. So here I'll just say proof sketch. So we'll just let a be a positive integer. Then we know that we can write a equals ak, or let's call it an. So we'll do the decimal expansion of it, an times 10 to the n plus an minus 1, 10 to the n minus 1, and so forth, down to, how about a1 times 10, and finally plus a0. And so what I'm going to do with this is each 10, right, I'm going to write as 11 minus 1. An times 11 minus 1 to the n plus a sub n 11 minus 1 to the n minus 1, a sub n minus 1, sorry, dot, 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 a1, 11 minus 1 plus a0. And remember from the previous slide that, so for each one of these terms, so an arbitrary term like this will look like a sub k, so I'm discluding this one, don't worry about a sub 0. A sub k, 11 minus 1 to the k, looks like, it'll look like 11 times a sub k times some constant, I'm going to call it z sub k, some integer, plus y to the k. So that would be negative 1 to the k, a sub k, times that. Or why don't I do this? Plus negative 1 to the k, a sub k. Remember how we could do that from the last slide? We break it up as some multiple of 11 plus this y to the k, but in this case, y is negative 1. And so negative 1 to the k right there times a sub k. And so for each one of these, I'm going to do that. So this is going to look like a sub n, no, let me write it like 11 times a sub n times z n. And I'm going to do it in columns here, plus negative 1 to the n a sub n, plus 11 a sub n minus 1 times z n minus 1. Again, I'm just keeping track that these are all multiples of 11. And then 11 a1, and then I'll write a0 down here, plus a0. And then each one of these, right, they're being split up, so this will look like, the other side of this will be negative 1 to the n minus 1, a sub n minus 1. And then this one plus negative 1 to the 1, so just negative 1 times a sub 1 plus a naught. So think of each one of these, right? I add them together, I get this thing up here. Add these together, I get this one. So it's similar to what we did last time, only now I'm splitting up the 11 minus 1 and using this fact up here. And now we see that, right, it's very similar to the last one. We see that each of these now is a multiple of 11. And so I can pull 11 out of that entire thing, or 11 divides this whole sum. And so the result we get from this, applying the star and double star again, we see that 11 divides a if and only if 11 divides, right, all this stuff up here is a multiple of 11, so I just care about these negative 1 to the n's here, down there. So if 11 divides this sum, and what is this sum? Well, it's over k equals 0 to n of negative 1 to the k, a sub k. So if I just do that, if I add up that bottom row there, that's what I get. And this is the same thing. Let me write it like this. This is the digit sum of the number a. So that's what's going on here. Okay, that's it for this one. Join me next time where we'll talk about primes and apply some of these divisibility rules.